Well, it's starting to rain on me here. Obviously, I'm inside, so I'm safe, but I don't know how much rain noise you'll hear. If I lose power, that's going to get interesting, but we'll go for a while here and see how it goes. You may not even know. I might have just not had said a word to you, huh? All right. So we talked about phase changes. We talked about the critical point on a TV diagram, temperature versus volume diagram. Now, if we were to plot, and again, these are diagrams from our text here, Changle and Bowles. Um, if we were to plot the temperature and volume values for all of the saturated liquid, that's these guys over here. All right, these are for saturated liquids over here. And if we plot those same temperature volume values for the saturated vapors, that's this side of those phase changes. Right? And then we connect those two data sets, right? So we connect the dots for saturated liquids all the way up to the critical point. We connect the dots for saturated vapors all the way up to the critical point. We get this dome region. That dome region has a name. That dome region is what we call the saturated mixture dome or the saturated dome. That everything under the dome is a mixture of saturated liquid and saturated vapor. If you're on the right-hand side of the dome, you're over here on the right-hand side of the dome, that is right on that line is purely saturated vapor. Everything's in the vapor phase, but it's right there at the saturation point. Same thing on this side. If you're right here on this side, that's the saturated liquid line. That means you've got boiling liquid at any point along this line here, all the way up to the critical point where we no longer observe a phase change. Okay, so that's TV diagram. Notice lines of constant pressure going down and and flattening out and then going down, or basically, I guess if you're increasing temperature and volume, it's going to go up and to the right and then flat and then up and to the right. And it doesn't matter what pressure it's at. That's what we're going to see there. I got to let my kid hang on. Everybody remembers Lucy. She had to come say hi. All right, go play. I'm in the cat's room recording videos, so they want in here every once in a while. Okay, this is a TV diagram. Okay, temperature versus volume diagram. Now we can also have what we call a pressure versus volume diagram, PV diagram. Very similar to the temperature versus volume diagrams, the TV diagrams. The only real difference here, of course, is that you're going to plot now lines of constant temperature. The third property, when you're comparing pressure versus volume, then I would also want to plot how the temperature is going to affect us. And the only difference between the TV diagrams and the PV diagrams is notice as the volume increases, these lines of constant temperature go down and to the right. Okay, so that's it. Otherwise, they look the same. You've got your dome region, you've got saturated liquid on this side, saturated vapor on that side, and you got your critical point up at the top. Okay, I keep forgetting to start my timer, so we're going to be somewhere in the neighborhood of 15 minutes on this video. That's okay. So I've got my timer going now. All right. Such an amateur tonight. I apologize. Now, if we continue looking at PV diagrams, pressure versus volume, again, I'm using diagrams from the Changle and Bowles text. Um, Notice that if we add solids to our diagram here, so now I've got these regions over here beyond to the left of the liquid. We've got this region here between solid and liquid, and then you get in this region where it's purely solid. And then you've got an area down here underneath your saturated dome where you've also got a sublimation dome. You've got the difference there, the area where it goes from solid to vapor, and a mixture of the two. Okay, so in that, this is for substances that contract on freezing. That is the overwhelming majority of most substances that we know of. But there are a few substances that will expand on freezing. So things like water, for example. I think molybdenum and a few rare earth metals. There are some substances you can go look up that do expand on freezing. And so if they do that, it kind of, the reason for these dotted lines is there's kind of a wrap around a little bit of kind of this region that overlaps over these other lines. So it's a little easier to see when we see it in 3 dimensions. Okay. Now notice on both of those diagrams, down here between the liquid vapor and the solid vapor region, you've got this triple line, right? You've got this triple line here. That shows up on both of these. Notice what happens when, so what is that? Well, let's talk about what that triple line represents. That triple line represents a known pressure, temperature, volume, where all three substances can exist in equilibrium. Or I'm sorry, all substances can exist in equilibrium between all three of those phases. It's not that I don't have molecules that are freezing or molecules that are vaporizing. It's just the number of liquid molecules that are freezing is equal to the number of solid molecules that are liquefying, melting. And the same thing in the vapor phase. I have a situation where not only is the solid and liquid in equilibrium, but also the liquid to vapor transition is in equilibrium. I have as many molecules condensing as I have vaporizing. That's what we call the triple line, or at least there's actually what we call the triple point, which is what I just described there. So that the triple point, and what happens is if I view the edge of a line, for example, right? So notice I've got a line down here between, again, the liquid vapor, solid vapor phase change regions. If I look at the end of that line, you get a single point. Right? What do I mean by that? I've got my cheat sheet here, and notice, so if I say, hey, this is basically my dome region. This is my dome region, and if I look at this line, this edge down here along the bottom, if I look at the end of that, notice what happens. If I get this nice and straight with the camera, I don't see this edge. If I get it nice and straight, all I see is this very point right there. That's what I'm seeing at this triple point right here. If I look at what we call the PT diagram, that's pressure versus temperature. This vaporization line, that's basically, you're looking at the dome region, you're looking at the side of it. You're looking at the edge of it. And down here at the very bottom is your triple point. That's the division between the vaporization and the sublimation domes, basically, the curves. Now, I've got a video here, and I've asked for permission to use it. I'm hoping they don't. I'm hoping that the author doesn't have a problem with it. I feel a little odd showing you a YouTube video inside another YouTube video, but guys, this video, this guy, this content creator just nails showing what that looks like, kind of what it looks like, because it's, yeah, can I kind of describe what this looks like or what the critical point looks like? What does the phase change look like? And I do want to show you, there's this guy that does this with dry ice, just so we can kind of see a little bit about, it's not a perfect description of what I'm about to describe here, but carbon dioxide, dry ice, right? Dry ice, that's carbon dioxide in the solid form. The triple point of dry ice is up here at 5.1 atmosphere. And it's out here at a temperature of minus 57 degrees C. Now, when we go buy dry ice to use it for like freezing things rapidly or keeping things really cold, that's occurring down here at 1 atmosphere. And then it's down here that's all the way down here at minus 78 degrees C. Now, I've not drawn this to scale. I don't have to. It's just for representation. But you can kind of see when if you've ever messed with dry ice, it goes from a solid, then it just disintegrates. It just literally vaporizes. It's not up here. It's actually doing what we call sublimating. It's going from a solid to a vapor. That's what we see at 1 atmosphere. To get to where we would even see liquid carbon dioxide, we've got to be at least at 5 atmospheres to get up here to where we see this liquid region even begins, or the change between liquid and vapor. And I'm going to cue this video up here. I need to shift some things around. I think this is going to play here. Let's see.
This is just a bunch of dry ice, and it's basically just solid carbon dioxide. What I think is interesting, though, is what happens if I seal some of it in a pressure chamber. Normally, dry ice just sublimates and turns directly into a gas, but here, it's actually able to melt. This is because the pressure in the chamber is able to build up, and once it gets above around 75 psi, the liquid form of carbon dioxide is able to exist.
It's about
What's
5 atmospheres.
cool is what happens if I heat this whole thing up with a hair dryer. All the CO2 eventually goes supercritical, and it turns into something that's kind of a
How
liquid
cool
and
is that?
gas at the same time. If I then cool it down, all of the liquid CO2 starts coming back, and I can't help but feel like this kind of looks magical.
How cool is that? Right?
This is just a bunch of dry
You're
ice.
right. So I'm hoping, since I'm not monetized, I'm hoping I don't get flagged on this video for showing you a YouTube video of a YouTube video. Because I'm not monetized. I'm just doing this for educational purposes, and I've asked for permission. Hopefully it doesn't get flagged. But if that works out, I wanted you to see that. I'm going to put that, even if I had to remove that portion or re-record this video, I'll put this link in the description for you. But it's just such a really cool. He's showing you basically going from down here, riding all the way up to the critical point, and then back down. So it's just really cool. It's you can't. It's it, it it would be really difficult for me to replicate that in a classroom setting or even here in my home trying to do that. This guy's done that beautifully. So go check out his channel. It's man, it's just really, really cool. Okay, let's continue on, shall we? So, what do we, and it's a really good representation of what we've got right here. This is what happens when we look at pressure, volume, and temperature in 3 dimensions. So we've looked at, here we're looking at pressure, temperature, we're looking at one side of it, right? If we go back, I'm looking at pressure and volume, another side of it. And previously we looked at temperature versus volume. If I throw all three of those into one 3 dimensional surface, this is what it looks like. This is for substances that contract on freezing. This is most normal substances with the exception of water. Right, so this is what it looks like in 3 dimensions. Now, if I look at the sides of this is kind of what I was describing earlier, where a line goes to a point if I look at the edge of it, right? So if I look straight up the side of this, right? So if I look, and some of you guys maybe have had engineering graphics and design with me where we talk about 3 dimensional theory, or some of you maybe have had like calculus 3 where we do you learn about calculus in 3 dimensions. So maybe this is a little bit easier, but basically I'm saying if I look at the pressure volume edge of this, if I just look right up the side of this, I'm going to see these surfaces here, right? And it's going to look something like this, kind of a flattened view looking from this direction, right? But if I look straight down, so if I look straight down, I'm going to see this. This is my temperature axis right here, same as this is my temperature axis. They just labeled it over here. This is also the temperature axis right here. And my volume is down here. So basically, I'm going to look straight down at this thing now. And really what they're showing here is just kind of this region, the saturated dome region is what we're seeing there. Right? And again, if I look at the edge of that, if I take a sheet of paper, so if I look at the side, if it's slanted like this, if I look straight down, I see the side like this. Or if I look right straight at it, I kind of see a side also. But if I look at the edge of that paper, I just see curves. And that's what I see when I look at a PT diagram. I don't see the dome regions when I look at the temperature and pressure. I'm looking at this side. I just see this edge of the dome region for saturated liquid, saturated vapor, and I just see the edge for solid vapor, right? And that's what you're seeing here. This is the saturated dome. This is the sublimation dome. That's the solid vapor dome. The triple line is this triple point between them, right? And so that's how it looks when we wrap all these together in 3 dimensions. Okay. What does that tell us? I'm going to go ahead and wrap this up because I've only got a little bit more to go. And in the next video, we can take a quick tour of property tables in the back of our book. So what does this mean for us? If I can figure out where something is located on this PVT surface, that means I figured out the state of that property. And state is something we quickly define in chapter 1. It's one of those terms that said, hey, it's in your book, go read it. State means once I know the state of a system, I can define all the properties of that system. So if I can figure out where my substance is on this PVT surface, that means that I've got models available to me that will tell me also its internal energy, its entropy, which is going to allow me then to do first and second law thermodynamics analysis on that system. And I can actually find unknown quantities like heat transfer or how much work is required to get from one state to another. Okay. So that's where we're headed. But chapters 4, 5, and 7 and 8 later on but we've got to get through chapter 3 first, which means we've got to learn how the property tables are going to describe this guy right here, this PVT surface. So that's really the good news is if you don't like Steve, I don't graph in 3 dimensions, or I mean, I learned that maybe in calculus class, but it's fine. It's fine. We're not going to graph in 3 dimensions. But this is all we're going to see are property tables, like this massive table of numbers. This is what it's describing, is this surface right here. Those tables are going to go on for pages and pages. It's describing this phenomena right here. So that's where it comes from. Okay. And that's what I'm saying here. All right. So I'm going to stop here and we'll pick up the next video from here. Okay.